Okay, and I'm just a rebel. I don't even care if it's streaming or not. Oh wait, I probably do. Anyway, good morning. Why am I so happy? It's sunny again on a Friday. And we're doing missing data. One of my favorite topics. What do you know about missing data?
Don't have it.
Oh, that makes life a little bit easier.
Yeah.
Oh no. Where do you learn missing data in our curriculum? Oh no. We got to work on that. Where do you learn missing data in our curriculum?
You'll see some in meta-analysis, maybe a little bit in design.
I waved my hands at it for like 10 minutes.
So let me think. Who teaches meta-analysis?
That guy.
And who teaches design?
That guy.
Oh my goodness. Ariel brings missing data to our program. No, I think we need to have you could teach a whole semester-long course on it. Maybe even more than that.
I don't think you should though.
When we teach multivariate, we usually put some missing data in multivariate as well. I can't go into all the concepts of missing data, and I saw the book chapter for our book this class, and it was like a miniature Craig Ender's book, but didn't have a whole lot of Bayesian in it. So I'm just going to try to be straight, try to be Bayes. I'm going to ignore all of the details about missing at random versus missing not at random and blah, blah, blah. We're just going to assume the data are missing at random.
You don't have a choice. That's it.
Yeah, so when we assume that, then we can use Bayes' method to make this work.
Have you used the factorization theorem to check the ignorability of the data?
Fuck the factorization theorem. Sorry. I've sort of now I stumbled accidentally last week when we were talking about epistemology. I think I stumbled into just saying that for everything I don't agree with. So much easier than actually making an argument. Oh, fuck that. I don't care about this. So your data are missing at random. Does anyone know what that means? Okay, cool. Which just it's such a silly thing. Missing at random versus missing completely at random versus missing not at random. It's such a kind of a ridiculous amount of whatever. So if you look up the word missing from the JAGS user manual, literally go click on that link and hit Control F and type missing in. There are precious 3 times in the entire manual the word missing shows up 3 times. 3! Makes you think, well, JAGS doesn't do missing very well, right? But it couldn't be further from the truth. In fact, Bayesian methods for missing are already in JAGS, and they're well established. They just don't talk about it, or I don't know what. Did you cover Bayesian missing data?
No.
Okay.
I knew that you were coming, so I didn't.
No, right. No, I just want to make sure. I don't want to be like, well, whatever Dr. Alloway says is true most of the time.
Can you call my wife?
Well, no, that's an extra charge. That costs extra. So we're going to start with a simulation to sort of show what happens in missing data. It's a ridiculous simulation. And I've decided to set my number seeds over famous numbers that I've heard in my life, just randomly. So 007, this is the James Bond. Not that I've ever made it through an entire Bond movie. So
The Daniel Craig ones?
None of them. I know, it's terrible. Should I even be here on Earth, let alone teaching this class? But the probability that I believe a movie is good is about 0.02, right?
That's conservative.
So yeah. So we're going to generate data. We're going to generate 1,000 observations because I really want to show some real good signal and data as to what's happening with JAGS. We're going to sort of deconstruct JAGS to show how it's working with missing data. We're going to generate a binary outcome that has a 50-50 chance of being 0 versus 1. We're going to think of this as like a t-test type design. 2 samples or single sample or 2 sample t-tests, 2 groups. We're going to do mean difference, but we're going to do it in a linear model. Here we're going to set beta 0. So we're going to create a regression line of y given x, where beta 0 is 10, beta 1 is 10, and the residual variance is 1. So you can see there's a big signal to noise ratio in the data, and I want to do that. So I'm going to generate x from a binomial, a one trial binomial, generate y from a regression line, and I'm going to make the very first observation of x missing. Could have done the same thing with y, but we're going to do that with x for right now, okay? Because missing predictors, that's harder to do in a lot of the ML programs, right? So take a look at this ridiculous distribution I just generated. Why would I'll ever generate a distribution that looks like that? What can you tell me about x? And so now you can say what you can say about y from x. It's pretty clear. But what can you tell me about x if you know y? Let's flip this around. Let's make ANOVA the discriminant analysis. You get that in note the derivative, right? Maybe, sort of.
Unfortunately.
The concepts are good. What do you know about x from y?
Well, essentially, if you know y, you know x.
Ah, that's exactly it, right? If you were to go and put a dividing line somewhere in this little gap, if y is greater than wherever that line is, x is 1. If y is less than, or equal to, I guess, y is 0, right? That's good. I wanted to do that because I was thinking about coming up with a simulation design to let me know what JAGS is doing, because the precious 3 words were in the manual. But what should happen, though, in my head what I was doing was trying to trick out JAGS, because if I ran 2 models to see what it did with x, I ran x by itself, or I ran x and y with no slope, right? I should see that the x1 that gets imputed should be about 50-50, because x will have a distribution and it will only have that same distribution to put in. However, if I put x and y in, it's the JAGS police, they're calling it gay. Actually, I have a 312 area code number that calls nearly every day. And
I got that call this morning too.
some of, but they leave a message, I think it's in Mandarin, right? And Google can't translate my message for me. And so I don't know what this is. Yeah, anyway, you got a 312 as well.
312.
Chicago.
Chicago, yeah.
Yeah.
100%.
Anyway, if I, so again, condition 1, x by itself should be 50-50. Condition 2, x and y together. What we should see is whatever x was should really show us where it is. Because what's happening in Bayes, what should be happening in Bayes and what should be happening in JAGS is the following. Right? We can create a model for x where the probability of x is just this pi term, pi sub x. And then a model for y, right? So this is essentially a Bernoulli or binomial distribution that I'm implying there. For y, we have our regression, conditional, normal, so on and so forth, right? Here, we can use but if we're trying to figure out what the distribution of x is to go and do Bayesian missing data, that's where the combo starts to come in. If we wanted the distribution of x given y, what Bayes is, basically, if we're going to go and take pieces of x and figure out what the missing data distribution might be, we can use Bayes' theorem to put the pieces together. Here, y given x is for x given y is proportional to the distribution of y given x, which was given by our regression, times the distribution of x as a prior, which was given by our distribution of x. So we've just done a quick little Bayesian flip, but it absolutely implies what x should be because of the joint nature of the algorithm itself. It doesn't sound like it's complicated, but that's actually really cool. You think about how powerful that is. It's like, oh, you have missing data. Did you specify the distribution of the data? Great, I got it. I'll take it from here. Thanks.
So if I'm translating, it sounds like if you just tried to do the missingness with x all by itself, that would be missing completely at random. Whereas if you're throwing y into the mix, that's the definition of missing at random.
That's right. That would be it.
And so this is why it's like, it's okay to do this because you're assuming that all of these distributions are accurately characterized even though there's missing data and you're just sort of filling in the points in them.
That's right.
I think what the factorization theorem will give you.
Oh, good.
No.
Don't make him angry.
I'm just messing
Don't
around.
make him angry.
Shall we run this quick little analysis? The factorization theorem, is that the classic factorization theorem? Yeah. Di Finetti. Yeah.
In Rubin's work,
Oh.
to make the argument of is that always what is ignorable.
Right.
So I go back to the factorization theorem.
All right. So yeah, this is exactly sounds like that. I am not a missing data expert. I'm just going to say.
Does normal mean completely at random?
No, missing at random.
Yeah.
That it means missing normal.
Yeah, non-ignorable data is missing not at random. Which actually you can do some fun things with that here too. Sort of. If you know sort of where the missingness mechanism is related to, you can create a Bayes model for just the missing data for all of that and have it imputed as well. But so what are we going to do here? We're going to take, we're going to do this together. Together meaning x and y jointly. So this is a very simple likelihood function. X is feels de Bourne, as I think we said in here, and y is de norm. Still waiting for that candidate to get into the race. Then I'll have to ask her like de Chai and or de Kai. Never mind. Today we're going to find a new one, de Dirch.
Look at that guy.
Yeah. The misspelling of Dirichlet?
You know Dirch?
That's right. Hey,
I'm
Dirch.
not going to say what that sounds like.
So we're going to say that the probability pi, I'm just going to give it a uniform distribution using beta, really. It's a conjugate prior. I'm going to use a gamma, sigma inverse, put 4 and 8 for the parameters, just the heck of it, just to keep it stable. And beta 0, beta 1 have a really uninformative prior. Here we give it some data, we give it some parameters, but we're also going to track the values of x1. That's the missing piece of data. It's well, in this case, it's going to be a 0 or 1 variable, right? Which is also somewhat, I picked this one to be unique because some of the other things that you see, and not as much anymore, but in the historic missing data, people would sort of fill in categorical variables with non-categorical entities, which was not a great plan, but you know. So we ran this. Let's take a look at convergence, shall we? Did it converge? Whoa, where'd it go? There we go. Our hats are pretty good. Things look pretty nice. I'd say that's converged, wouldn't you? And wouldn't you know, here are all the values of x for the missing data that it imputed throughout the chain. So every step of the chain, for all the missing data in x, or y in this case, it has a step that says, oh, hey, you're missing. I'm going to draw a value of x from this posterior distribution that I think should be related to x and y. Put the value in, and then the next step of the chain to do the linear regression. What happens? It takes the complete data with the imputed x. So every step of the chain, it's imputing a value of x as it goes forward, based on the model itself. That's a big distinction. What do you think, Lisa?
I'm very happy about it.
It's pretty amazing, right?
Well, it's multiple imputation done simultaneously.
It is.
And then you avoid all the stupid decisions about how many imputed data sets and how do we combine them.
Well, I'm stuck thinking about the parallel and multi-imputation in the pooling part. Because in the pooling part, if you do it properly, yes, you will feed your model how you're doing in each one of your data sets separate, but then you will tweak the variances, yes?
Right.
To add the extra uncertainty of the multiple imputation. Here you don't have to really worry that much about that because the extra variance, even if I'm right, please correct me, it sounds as a statement, but it's a question. The extra variance is already there by being treated as a random variable.
Watch this. Can we do this real quick? Let me do some plots. The extra variance gets absorbed into the model posterior distributions, what should happen. I found, by the way, in doing latent class analysis, something I should have figured out long ago, but I didn't. Come on, why aren't you opening? Like, for real? How about we open? There it is. Okay. It was the Mcmc Plots. Have you seen this package? If you have, by the way, if you have advice for me on better things than doing in R, I'd love to hear them. Like Mcmc Plots takes a second to load, but it makes plotting objects out of JAGs a lot easier.
Oh, I like that.
Because you remember that we had to do the trace plot deal to like make things work. The plot that It's a triplot, or here, let's do this. So what I want to do is plot some densities. Den plot is what it's called. And you give it the model JAGs, and you could actually limit it to certain parameters of names, like beta, right? So here, well, let's just keep this real. There we go. All right, so here are the plots. See, look how easy that was. It makes nice looking plots and everything. It uses ggplot. So here's our probability across our four chains. Here's beta 1, beta 0. Sigma has a very small, once you get past burn-in. Why I'm doing that is what I want to show is if I change my simulation slightly so that instead of x1 is missing, but let's do x sample x equals 1 to 1,000, or number of obs, size equals, let's make 400 missing just because I hit 4 instead of 5. And replace equals false. What this code right here will do, this sample code will just randomly draw 400 observations from, pardon me, I kept the bracket there. Draws 400 observations from at random from the set that we gave it. So now we have, what we should see with this plot is that the variance, what you're talking about, the pooling, where you typically see an expansion of variance, you should see that in the analysis itself. And, okay, let's do this. Nope. Beta 1. Well, I don't know if that's better or worse, but actually what I should have done was save this as big miss. All right, let's save that. Then we're just going to look at the posterior variance. Sorry, folks. Donk. The good thing is this runs pretty quickly with this sample. All right, so beta 1, the posterior variance of beta 1. Here, with the small missing is, here are your posterior variances that you see. And then what do I want to look at? What we should see is the variance is bigger. Doing this, yeah, there we go. So the variance gets bigger in what we have. We still have a tremendously huge signal in our data because of the way that we generated it, x and y are tremendous. If we reduce the signal, you'll see it much more expansive. But what I'm trying to show you is what you thought was, instead of pooling, a lot of times you impute data, you run a bunch of analyses, and you pool them all together at the end. This is the imputation in the middle of this is allowing it to continue that error throughout. What's that?
This is cool.
It's much better. Well, this is why I'm shocked, because JAGS has 3 words. The word missing shows up 3 times. It's like, dude, do you realize there's a whole industry in our land that's built on this, right?
Oh, yeah.
So it's like, yeah, missing. Oh, we did that like years ago. What's the problem? It's like not even a thing anymore. Like, what? So
definition would say that's a solved question.
that's right. But what could go wrong under this approach? Let me ask you that. Although we're not likely to see it in the regression case. But actually, think about that while I want to show you this next example. This is the example where effectively I had the same syntax from before, but I set beta 1 to 0. So it's effectively sampling x and y, where the prior for x, or the distribution for x, is the only thing impacting it. This is sort of my test to JAGS to see if it's working the way I thought it was. What we should see with that, you see, this isn't what I expected it to be. What happened? When I did this at home, X was 50-50. Now X is all 1. What am I doing wrong here? Anyway, beta 1 is 0. They set X to be 1. Very interesting. Whenever I did this in my example, if you pull up the HTML online for this, you'll see here. When I was at home, and let me double check here. I hate feeling stupid like this every morning. All right, here we go. There we go. See, in my example, with this syntax, and I don't know I know what's happening because I switched my data. X1 is not missing. That's why it's 1 all the time. Let me go back and I'll fix it back and show it. Let's see, take a look at this. This is the result from before, and I'll go back and run this again. Beta 1 is fixed to 0, there's no variance. X1, which was our missing piece of observation, is roughly 50-50. That's because it's actually exactly 50-50. That's because pi is roughly 50-50. That's our proportion of values of X. It's 1 versus 0. So what I'm saying here is sort of trying to demonstrate some ways that you have to sort of trick your software to figure out what's going on under the hood. This is that. So if I go back and let's just do this, X. There'll be 2 pieces of missing data now. And I go here, just to show you that I'm not just lying. Trust is important. There we go. Ah! I'm doing something wrong again. Trust but verify. You know what? I didn't load up the data. I used the same data as model 01. Model 01 with X then had X being, well, it's a 1 also. What the heck have I done wrong? God, today is just becoming a big mess, isn't it? There it goes. Okay, so X1, when we include Y, is almost always 1. In fact, there's 1,000 simulated observations, keeping 999 of them are X being 1. And then when I don't include Y in the likelihood for the prior, X becomes close to 0.5. And you'll see X and pi tend to mirror each other, and that's because pi is the only thing that's telling you X. Right? So I think it's pretty cool, pretty slick. What could go wrong? Although you don't see it here, just because this is a really, really easy example. I guess you could actually.
You have to have a distribution for X. People aren't used to thinking along those lines.
Also, that's true. You have to have the distribution. The distribution has to be right.
Yeah, that's what I mean. The right one.
What if we had truly a quadratic or curvilinear relationship here? We estimated the model that was linear. What do you think it would look like if we had a lot of missing data when we imputed them?
Linear.
Do you want to find out?
How can you have a quadratic effect with a binary?
No, but if we had an X and Y that was, I could create a continuous. You want me to show? Can I show this? This is a pretty simple example, but I think I can do this quickly. I know. Oh, watch this. Let's see how quickly. Code, Templin code. Yeah. All right. Someone set their watches, and also, can someone tally up the number of times I swear? All right. Let's see here. Sim data reg 2. Let's imagine we have, let's say 400 missing again. Now we're going to have mean X equals, let's say 50, SD X equals 10. Is that like the t-score or something like that? Oh, yeah. I don't even know what a t-score is. I got lucky there. We're going to R norm X. And we're going to create a quadratic relationship between x and y. Sound good? And because, Lisa, what are good slopes for quadratics? Totally forgetting, like, off the top of my head, I'm not going to be able to generate these.
Twice the quadratic is how the linear rate of change changes per unit.
That doesn't look curvilinear. Oh, that's because beta 2 times x squared. That's what I need. Yeah, okay. That's, yeah, I want it more steep, right? So if I bet a bigger quadratic slope, that would do it.
Ask these kids. What do they think?
What do you think? How do I make this a more steep curve? I want more bendy.
Yeah, call on him. He's capable.
Yeah. So twice the quadratic is the linear rate of change.
No.
Oh, sorry. Instantaneous linear. It's the tangent line, no?
No.
No. What is it?
Ask him. I
Hey.
already have my cage.
Somebody help me.
What is Batman when you need it?
Twice the quadratic is how the linear slope changes per unit x.
Mhm.
So yeah, you need a bigger quadratic if you want to.
That's where I was going with that. I was going to do this. Let's just make it super big.
And make it a smaller linear slope too, and make it more U-shaped.
Okay, let's do 0.
Well, that'll do it.
Nope. Is that enough? I want to make it like an actual parabola. How do I do that, folks?
Like that.
Yeah, this is showing my on-the-fly lack of skills with this. This is a little out of my league. I bet if I read it, I could find it. Range of x, is that a problem? Range restriction? Do I need a bigger variance of x? There we go. All right, let's do that, shall we? What could go wrong? Okay, let me go back and copy model 1, all this fun stuff. Okay, model 1, instead of deburn, we're going to do denorm. We're going to do mean x, actually, denorm mean x in sigma 2.inv x. And here, to make it simple, we're going to say mean x is this, right here. Sigma 2.inv x is d gamma, and I'm going to give it the variance of x, like that. And let's see here, lower degrees of freedom. So what could happen here is basically what we're trying to get to. Everything else looks fine. We're going to fit a linear model with x. We don't need to give it any extra data. I fixed all that, but let's monitor. We don't need x1. We know how it's going to impute. X is going to be continuous, right? And here we want mean x and sigma 2x. But we don't have pi anymore. All right, let's see if this will fly. Could it possibly be? Did it run? Hey, I think it ran. All right, how am I going to get plots with this though? Not really. Beta 1 though, beta 1 is very, very negative when I set beta 1 to be a 0, right? Beta 0. Beta 0 is right at 0, but beta 1 is very, very negative. So what's happening?
Seeing this part of the actual relationship, and it thinks, oh, okay, so it's just a super negative linear relationship.
That's exactly right. Right? I tried to fit this line, right, to our quadratic data, But what was happening was reinforcing it. Let's see, do I have our data somewhere up here? Actually, no, the data are right here. Anyway, we've got this plot for our data right here. And we're fitting a line right to it. So it's going to look something like this, right? And so whenever y thinks, oh, I got an observation here, it's missing, I'm going to go and fill in that value, it's going to fill in the value based on linear. And so if we were to plot step by step in the chain the imputed values of the chain of this.
Actually, can I ask a question?
Yeah.
I actually have not understood why beta 1 is fixed to 1.
Say that again?
Why beta 1 is fixed to 0?
0? Oh, I'm looking for simulation parameters that give me a nice curve. What I'm trying to show is when your model is wrong, when you use this method to impute data, you're going to impute data to make the model more confirmed. And so with this, with picking beta 1 at 0, it resulted in a plot that looked like this for our data. This is the true model. If I change beta 1 to something else, it may not be as flat. I was just looking for combinations of beta that would do it.
So it is not to estimate truly beta 1.
That's right. No, it's more to show what happens when our model is bad, not working the way we expect it to. I'm going to track x. Let me see if I can give a scatter plot of x at every step of the chain, because what it should do with y is be able to tell us x and y throughout. Actually, x is lowercase, y is lowercase. Let's do this. It'll be a big object that we can get back. Let's see here. Taking a little bit longer. There it goes. Okay. Let's see if I can do this plot well. I'm going to dig into the posterior here. We're going to grab the column names of the posterior matrix. There we go. We have all the x's and we have all the y's actually too, right? So we know that there's 1,000 x's and it starts at observation 7. So I say x, let's take the 500th simulation, and that's going to be equal to, nope, let's do this. This is the 500th iteration, and we want values 7 through 1006th, right? This should give us all the x's. There we go. There's all the x's. And plot. We are now going to do y as well. I'm just going to show what y looks like. Did it work? There. All right. Can you tell what the missing data is versus what the observed data are? Right? This could go wrong. To do things well in this method, you have to get the model right. Otherwise, guess what? Your model starts, you got a lot of missing data. Missing data are going to look like your model. What do you think about that? Should have thought of that plot earlier, but it's tough for me to I gotta get through the nervousness of getting a lecture together before I get back.
This is the same thing that happens in multiple imputation though. If your imputation model is incomplete, like it has to have everything in it that you would ever want to look for in y.
That's right.
So to solve that problem in multiple imputation land, certain scholars have suggested throwing your entire data set in the imputation model or principal components derivations thereof to sort of cover all your bases.
Well, there's other methods that are done, the chained equations method as well. Although chained equations on this, mice, is one of the ways it does it.
What is that exactly?
So if you have multivariate data, basically you use every other observation to predict each. But if you think about it, but it's a linear prediction if I'm not mistaken, right?
Probably.
So here it would be doing the same thing, right? So the other forms of missing data, if we could hack into JAGs, we could use them too. What's the term? Hot match. Where you look at y and you pair a y with an x and you find the closest y that's observed to each of these missing. and you pair those x's with them, right? Or you find a neighborhood of y by x, and you randomly pick and do that. That would solve this problem here.
That seems a reasonable approach, right?
Well, yeah, it can be, and that's actually what's happening in the chained equations. Create a predicted value for each variable based on all the other variables in the model, and based on that predicted value, it takes a window around and randomly selects another observation with complete data by that, and imputes the value from that, roughly, if I'm remembering exactly. I may be wrong about my memory. So
You advocate something like that instead of throwing your entire data set in the imputation.
I like that approach. I'm not sure it works in all the cases either. You still have a large part of, there's still a model that's implied by it. And I think that's the part. Anytime you have a model, when you start filling in data based on model, you're going to have this problem. But here was a very obvious case to see it. I think this graph's pretty funny.
Yeah, it seems you can either choose a model for your data yourself, or you can let your data choose the model it thinks it's representing.
Right.
And I don't know if there's any other way to do it, right?
No, and that's exactly it. It's hard to, with missing data, you're kind of stuck. You're at the mercy of it. And so remember that, though, as we get into psychometrics. Would you like to see a psychometric example? Any other questions on this, by the way? Thoughts about missing in JAGs? Sounds easy. Got to get the model right. But then again, you got to get the model right for every analysis, right?
But this is even worse because you can make your model look more right,
Yes.
but it's cheating.
Guess what happens with model fit if you have lots of missing data?
And then you impute it to fit the model.
Yes.
Really.
Guess what happens?
Woo!
Boom.
Right.
Problem solved. If your data don't fit, just delete some observations completely at random and use JAGs. I'm serious. You're not going to bias it. Model fits.
For the best fit, have no data.
Yes. Rosh is smiling upon us.
Write that to the Rosh-friendly journals.
The cult of Rosh. I think like every other, I was talking, walking on hallowed ground last week. I'm sort of just looking to torch everyone.
Iconic class.
Yeah. Anyway,
Can I play devil's advocate
yeah,
for a second?
please. This is what this forum is good for. There's no sacred ideas.
I didn't know we get permission for that.
Well, no, I'm gonna ask a question that's gonna make me sound stupid, but I really wanna know the answer.
I don't know if I have the answer.
Because I'm not afraid of looking stupid.
I like when professors say that. It's like, it's like when a model says, "Oh, I feel kind of fat today." Me as normal person.
Oh, I feel so bad. You know? See, when you're in the professor head, all you realize are your weaknesses.
Sure.
So it becomes easy to say that, but you're right.
Well, I've developed, I wouldn't say I've developed, I have used a workaround before, and I wanna know what's wrong with it. Okay, let me just phrase the question that way. Because I'm pretty sure there's something, and, because it's too easy. So, in the extreme, think about a variable that is missing for a reason. Like if we have something, like you have men and women in the data set, and you have a date since your last menstrual period or something, right? Number of days since that, right? The men don't have an answer for that. Odds are good. You could impute one, but that's stupid, right? The better thing to do would be to treat that variable, days since last period or whatever, as a nested effect for women only.
Yeah.
So you would put that in as interacting with gender, where it only turns on when it's for the one group.
That's
right?
fine. Yeah.
So that strategy makes sense in that sort of thing. And it makes more sense than imputing a menstruation date for men.
Right.
Arguably. So in the limit, why don't we do that always? Why don't we fill in like a zero value for all missingness, but set up the model to say only if it's a real zero does it enter the model as a series of nested effects for every single variable, where the nestedness is whether it's actually present or whether it's missing and filled in to keep the algorithm right.
I think my answer would be not all models is that obvious to do. If we try to do that here, we effectively make it X and Y independent.
How?
In that case, if we do a nested effect for where the missing data happen to be, right? So the nested effect would show up this would only show up with nested, You're saying?
So what I'm saying is like, if you have, let's say, you have 400 of your x's that are missing.
Mm-hmm.
Like, let's go ahead and fill them in with a 0, but we're gonna make another variable for whether it's a filled in missing value or
Right.
whether it's a real
Right,
value.
right.
And then
Yeah.
we're gonna put the effect of x as interacting with real, meaning that it's only entering the model prediction if it's a real x. Otherwise, it's just being ignored
Right,
when it's
right,
fitting
right.
the prediction line.
Right here, right?
Mhm.
So that 0, when it shows up, when it's interacting,
Mhm.
is going to knock out all the terms and data for it, right? So basically, your predicted value is mean or intercept. Is that
It's
right?
only based on the real data.
Right. This would only be on the real data. That's fine. That's effectively like saying the data aren't there in the first place. Is what I'm trying to argue for.
Yeah.
Right. So you're basically eliminating the data in the first place in our case in this model.
Yes.
Or if you keep them and you allow JAGS to do its business with it, you're going to generate them based on the intercept of the data.
So in this case, that wouldn't make any sense to do because there's only one predictor and it's the same as listwise deletion.
Right.
But I'm thinking of this situation in which you have like a Swiss cheese.
No, I'm okay.
Missing
So that's what I'm saying.
some are missing,
Like, what I'm
some
saying
are
is that sounds like an appropriate approach, provided it's the right model,
Mhm.
and you have a situation where you can use it.
But you just said I have to have the right model to do this too.
Right. Right.
So we always have to have the right model
Yes.
when we have missing data.
Yes.
But it's the same as also in multiple imputation.
Mhm.
Yeah. That's
I'm just
basically.
saying, like, the goal of filling in the values is to get the right answers. It's not to fill in the values. So, but you're assuming the answers are right, even like you're filling in you're filling in the values to get the right answers, assuming those are the right answers to fill in the values.
Right.
So why fill in the values? Why don't you just run the model and get what you get?
The other part of it
So
is the
those
inflation of
don't
it.
drop.
The inflation of variance of your other parameters. So when you have the missing data, that should reflect more uncertainty in your analysis,
Mhm.
and that's what filling in the values are trying to do. They're trying to fill in and expand the variance of the parameters of the model that are supposed to be there.
But you're filling them in consistent with the model.
Yes, that's right. Consistent with the model.
So
Yeah, I know. It's a tough. There's no right answer.
how is this not cheating? Like I'm still back to that.
It kind of is.
Well, some people will argue that any treatment that you do to missing data is cheating.
Yeah, you don't have it. Like, you don't.
Right. Right, now I'm looking at the beta 1 distribution. It's very wide. Why is it very wide? Because there's a lot of missing data, things are wiggling around a lot. However, it still doesn't include its true value, which should have been 0. There's some type of negative relationship it's telling us, but we've got to look at our data to go figure that out. You're right. Yeah, it's a tough process because you can't just blindly do something with missing data is what it's suggesting. Perhaps I think your solution has merit in a number of cases, and probably more than just a number of them, but it doesn't work in all of them. So just like this doesn't work in all of them. And the thing about it is there's no missing data method that unlocks what the data should have been.
Yeah, you can't ever get it.
No.
So in your method, you're really saying you don't have the data, deal with it.
Right.
Yeah, I'm saying estimate the slope using the data that you have, but let's keep those cases in the data set so that they can inform other slopes for which they have real data.
Mhm.
Right.
That's what I'm trying to say.
The other methods seem to say, okay, we're going to assume some model and get some information in there, but it's going to be more information than we want because it's not really there, so we have to adjust that on the back end, either by adjusting variances or building in the posterior. They seem like two different approaches. I like that because any model we're gonna pick to fill in missing data will be way neater than the actual data would probably be in the first place.
Right, yeah. All right, other thoughts or questions? So I don't have anything wrong with it. It just depends. I think it's going to depend on model, and it's all cheating at some level.
Filling in something is cheating.
So if you're reading a paper and they're like, hey, missing data, blah, can be cheating.
Don't have missing.
That's the easiest solution. Just don't do it.
Don't do it.
All right, should we go and play with some psychometric data? You want to talk about cheating? Haha. All right, what the potential? Bayes is cheating to some people too, by the way. So And we're filling in data for Bayes, it's just parameters, but still. We're going to take our conspiracy data. I'm not going to show you the plots of them again. We're going to take the fourth observation and make it missing of the first variable. Why the fourth? You're going to find out in just a moment. We can do more than that eventually. So I did this, and I'm not going to show the syntax yet. I'm just like, yeah, you know, make it work. And Jags is like, no, don't like it. Something's wrong in its cryptic way. I was like, no, make it work. It's all supposed to be here. It's like, no, problem with the B's, man. You got B parameter issues. I'm like, no, I actually don't. They're all right here. Exactly. Does anyone know that reference piece? Do I need to play the video?
Right?
You might have to pull it up during break. Or now.
Yeah, right.
Whatever.
There's no better time than now. Always time.
Wait to wait some days that what you can accomplish now.
That's right.
Agreed.
You have to have the sound
One of the
on.
exercises that you're supposed to figure out what you would want to do if PC load letter. The fuck does that mean?
And then,
Then they take a baseball bat to it.
there he goes.
That's my favorite one.
Exercises that you're supposed to figure out what you would want to do if.
Back in the 90s.
On the way out so that they could take a baseball bat to it.
The Jags errors I get. So, turns out when you import data into Jags in a matrix, your data either has to all be missing or all be there. At least that's what I read.
How can you have missingness in a matrix that's all the way missing?
Maybe you're trying to generate data. I don't know.
Is that like the sound of silence?
So what that means? So that means okay. So before, when I would input all the data into X and pass it to Jags, when I made one observation missing, it was like, no, you can't do that. So I broke X into variables. Item 1, item 2, and to not overwhelm us with code, I only put 3 items in, just because. And then it told me there were more errors. Well, the only way I resolved those errors, there's probably better ways, I admit. I did a, only about an hour and a half search, not, 2 days. But the only way I was able to resolve those was to make my vector of parameters into single values as well. So item 1, remember these data, I'm going to use a graded response model for the data. There are Likert data, 1, 2, 3, 4, 5 responses. I'm going to break item 1, item 2, item 3 into sections, and in each of these, the code for the graded response model is going to show up. The only difference is for item 1, you see item 1 here, and each of the parameters are B1 and A1, right? Whereas for item 2, it's item 2, B2 and A2, and so on and so forth. The priors are all the same that I did before. And so let's have some fun with this, shall we? Conspiracy data. Hooray, conspiracies. And then we run our analysis. Takes a little bit longer. But basically, I deleted the observation, the fourth observation's data. It was actually a 1 before. I deleted it, made it NA, just to show what happens. It's running. Anybody else want to talk or comment? An experience with missing data you'd like to share?
Sure. When you add shit up, missing data is problematic.
Oh yeah, if you make a sum score out of this, what do you do with your missing data?
Well, I've troubleshooted this before with students who sum things up and some of the items were missing, and you know what? Those people had really low scores. And I'm like, yeah, you can't do that. It's like, but if you take the mean instead, it's essentially as if you're imputing the mean for those missing items. It's the same thing. And if there are reasons why people skip certain questions, and you don't have those reasons, then you're assuming missing completely at random, and you're doing single imputation for the missing items.
Wow. If only there was a better way.
I know, right?
Like a model? Like a Roche model? Roche is a little bit better? All right, it's done. Hooray! Should we see the results? It ran, but the thing I'm really interested in is the fourth item right here. Item 4, on average, becomes 1.672. And if I show you a plot of this is what the distribution of the missing looks like. So this is that fourth person, and throughout in the chain, what is JAGS doing? Well, because our psychometric model defines for each of the items a distribution, right? It's dependent on theta. This person's getting a theta to start out with, and then in the step where it tries to fill in the data, it uses theta. It uses the IRT model to guess what the person's response should be. And it draws that person's response at random from that posterior distribution, fills it in, goes and does the other steps in the chain. Pretty cool, huh? Pretty cool until you consider the following. Person 4, let's see if I can show the data for this person. Right here. Here is person 4. Okay, person 4 had a 1 for each of these. And we changed this to an A. Now, why I chose person 4 was because I quickly wanted to find another person with the same response pattern. And I wanted to show you what happened to the posterior distribution of theta in this case. It's kind of interesting to see what are the ramifications of missing data. They probably aren't too big. We only deleted one observation. There's probably not a big change to our item parameters, unless this is a leverage point, but with categorical data, we probably wouldn't have that. So now what I want to do, I just looked at the first 10 observations, try to find a similar response pattern. Here it comes to you. These people are absolutely not conspiracy theorists. They don't believe in these conspiracies. So what do you think happens to the posterior distribution of theta for this person when I delete that one observation? It's bigger, possibly. Let's think about where the mean goes. Where does the mean of it go? So clearly, this person should be at the bottom of this scale. They're at the floor. The mean theta for this should be all the way to the left, as far as this will let us go.
It has to go up, right?
Yeah. So when you delete this, think what's happening in the algorithm. At each point in the chain, what's going on is that you have the possibility, it's not just always 1 for this person, right? This is the case where that 6th person is, but now for person 4, we've got not 1. Exactly. So the center of this distribution should move over a little bit. And that's what's happening.
This is also kind of an issue because of the data, right? There's no way for it to counterbalance itself and end up where it was before because there is a 4.
That's exactly right. Exactly.
I'm saying what happened if they had a 5, then their theta goes down.
That's exactly it. So here, I wanted to plot the 2 posterior distributions. The complete data is the dashed one, and the line data is the missing one. And it turns out, here's one of the interesting parts, what's wider? The complete data is wider.
Cheating!
Why is it wider? It's really hard to determine where a person's floor is when they're at the bottom observation. In ML, this would not be identified. It's only identified in Bayes because we put a prior distribution on it.
So not only is the missing one that's filled in wrong, but it's more sure that it's wrong.
That's exactly what's happening.
I'm pretty sure I'm completely right in this. No, you're wrong.
No.
I'm pretty sure I'm right.
You know that item that you missed that you like all the other ones you're like, no, totally not a conspiracy. No, I don't believe it. No, I don't believe it. You sort of just got so tired of it you didn't fill in the first one, or you're like, oh my god, this doesn't even dignify a response. Just because of that, I'm pretty sure you're not as much of a normal person as this other person.
Only conspiracy theorists will leave this one blank.
That's right. So, what do you think? Interesting?
Cheating.
Cheating?
I'm back to cheating.
I didn't bother with model fit. Technically, these data should fit pretty close to perfect because of the way I only had 3 items to identify this scale. But interesting stuff, huh? sort of counterfactual things that can happen with the missing data. Is it making you think? Ponder a little bit? Just remember that thought. If you're ever in a spot in your job and someone's like, yeah, just fill it in.
There's no good way to deal with missing data.
Not really.
Unless you treat it as an answer.
Yes. Now, if we made that the 6th answer option.
Well, but then you need your semi-ordered thing that we were talking about last time.
Yep, that would be good.
Whether or not they answered the question is sort of like one option.
Give it its own parameter. That's right.
Its own slope and its own intercept, and then if they answered it, here's the rest of the graded response model, something like that.
Yeah, and I thought that would be given that I had to do this lengthy code just to do 3 items, I didn't want to do that.
I don't expect you to do that. I'm just saying that the idea that missingness matters and that people choose not to answer certain questions for reasons.
There's information in missingness.
Yeah,
That's right.
So like if you find some of the items are more likely to be missing, like that's information that you should use. You shouldn't just like sweep it under the rug, filling in random crap.
The whole line that you just said, the only conspiracy theorists would miss that item. Exactly. Missingness is related to theta is what we're trying to say.
And the same is true of not applicable or other like things where they can't answer your question for some reason. That's an answer.
So you having fun with missing data? You like?
It's slightly off topic.
Good.
Missing data.
Good.
Here to me, what makes my head spin around is in meta-analysis, people is using multiple imputation. When they don't have other studies, they are going to use information from other studies to impute that. It's like crazy talk.
Yeah, I think it could be. It could be. I mean, like, this is a person that we gave them a better score because of it. Not only that, we're more sure of our better score. Yeah. By the way, the other thing I was going to point out about this graph, it does a nice image. I don't know if you can see it. These distributions are skewed a little bit, right? Only had 3 items. But this is just a reminder that the posterior distribution for theta is not guaranteed to be normal. Sort of changes what we do think a little bit when we think that. Yeah, meta-analysis. That would be bad. I think. And what are your sample sizes for the other studies they're talking? Or how many other studies are being used to?
It depends. Sometimes you may have 100, but sometimes you have 20. Sometimes you may have 10.
Can you imagine what would happen if I cut down my sample size in some of these?
And sometimes it's not even that people are imputing truly study characteristics, are individual characteristics aggregated at the study level.
Right,
So
yeah.
like, how in the world do you really know that?
Yeah, it's pretty interesting.
Similar in mixed models, yeah, when people do the group level variables and they try to impute that. It's like, oh, how do you know that?
Clairvoyance.
Building on my sort of imputing menstrual dates for men is stupid idea. I was once at a cognitive aging conference, probably 10 years ago when I was used to go to those things. And so these are things where when in older adult data, if you're missing data, odds are good the person's dead or otherwise incapacitated and they can't do your study anymore. And so I remember sitting in a session where someone didn't even blink. They're like, we use multiple imputation. And then someone else was like, no, the data aren't missing, they're dead. Like that is complete for that person. That's all the data there were to be had. And like, this is crazy.
No, we asked them what they would thought about it. They were in the grave, or they were cremated, you know. We asked their spirit what they thought.
Yeah. But then the answer is like, well, if multiple imputation gives asymptotically equivalent results to full information maximum likelihood under the same imputation and analysis model, then how is it any more reasonable to use full information maximum likelihood when you have people who are dead?
Well, and the thing, this is where your idea of where you have to model it, put a model into it, is much more appropriate.
If you're alive, here's your slope.
Mm-hmm.
If you're not alive, peace be with you.
Mm-hmm. How are we doing? All right. We done with missing? Can we put missing to bed? Move on to the next topic. Ta-da. Going through all the hits, the next topics are mixture models. Lisa, how do you feel about mixture models? Anyone know that reference?
You're gonna have to play that. More recent.
No, that's not. That's actually, yeah, it's slightly more recent. Shall I play another reference?
Office Space was like 99 or something. Dave Chappelle was.
I was too young to watch it.
Hey. Oh man, hey.
So one of my colleagues in the field, one of my good friends and colleagues, he and I will send that clip to each other over text message almost always when we involve going to a conference. How was the talk? What about this topic? What about this person? Reference Dave Chappelle show back when I was in grad school. Play our haters ball. So if you ever want to look that up, go ahead. It's a bit of slice of Americana from 2002, 3? I don't know. And I'm old, right? So I went in grad school back when we used to have Fortran compilers. What is a mixture model? How many of you have learned about mixture models in any of your classes? Awesome. No, I'm just asking. I don't. There's no reason to have it. There's lots of topics that our curriculum isn't going to cover. So mixture models do show up from time to time. They don't usually show up in measurement until you get into the diagnostic model. So those of you taking my class next semester. By the way, I also want to tell you there's a lot of great class offerings. Lisa has one. Ariel is teaching design and experiment. No.
Yeah.
You've
Design.
already taken that one.
You've probably already taken design.
Clustered multi-level models.
There we go. And then anyway, just putting it out there because the university wants us to get enrollments in our classes. Just a heads up, that's all.
I feel like a lot of these topics, you just take different words for measurement and smash them together, and you're like, that will now be a topic that I'm going to talk about.
Kind of. It's kind of. It's really like a mixed bag. We use a hypergeometric distribution to come up with the class.
Cluster, mixture, diagnostic.
You know what the best part of mixture models are? Are mixed models. Mixtures of linear mixed models. This is the best because then you can double mix it.
No.
It's like a twice baked potato.
No, those are
Twice mixed model. Okay, so what are mixture models trying to do? Mixture models, in their broadest sense, in their most basic sense, are trying to figure out the number of classes you have in your data. We call them latent class. Latent class analysis is one of the very first mixture models. Actually, mixture models go back a long time. There's an 1890 paper with Pearson, I believe. They fit a 2-class mixture model to data on sizes of parts of crabs. Right? Kid you not. Wow, interesting, right? But it goes back a long time. The idea is that your data come from people who are in different classes, and your job with a mixture model is to figure out how many classes there are, discrete classes, and then what they mean. This is sort of an exploratory analysis way I'm showing you here. Which means, Lisa?
It's not your data's job to tell you what it's measuring.
Or hate.
Hate.
So we're going to use the Tatsuoka fraction subtraction data for this again. This is the finite mixture model. Finite mixture models are the big broad heading where things have sort of landed. They subsume nearly everything, unless you're an SEM, of course. This is a structural equation model. Sorry. The mission creep of the SEM world is really interesting to me. I'm going to find that fun now. Maybe not. Everything's in that structural equation model. Next week, we're going to do a multi-level structural equation model. Look at your face. We're going to do a multi-level model next week for longitudinal data that you could call multi-level SEM, but we're going to really show it's not really multi-level SEM, but we're going to do some Bayes because person mean centering, but the mean itself is with error, right? So we want to somehow have that in our model. Anyway, that's next week. This week, finite mixture model. What is this model trying to tell us? This is the distribution of your data for a person. It's saying the distribution of your data, marginally, come from trying to figure out if a person is in each class. The distribution of a person considering they might be in a class C, right? Well, that, using Bayes' theorem, or we're trying to figure out, this is a joint distribution, excuse me, right? You're trying to make this a joint distribution, we multiply it by the probability anybody's in that class. And to marginalize, we probably kind of get out of the way of it. So, what are the classes? These are discrete entities. So for any analysis, you have to pick a set number of classes. In our case, we're going to use the number 4. For most analyses, you will probably start with, are there 2 classes? I don't know. Are there 3 classes? I don't know. Are there 4 classes? Right, so you'll fit multiple models with varying levels of classes, but for each analysis, you pick the capital C, the number of classes. And what that turns out to be is that the distribution of the classes then is a multinomial variable, right? One trial for each person, multinomial. So there's a probability that someone is in each class, and those probabilities sum to 1. And I'm going to express that today as this eta C parameter. Some people in the mixture model world might call this the mixing proportion. But what that's trying to tell us is, overall, the proportion of our people that fall into each class is eta C, or for any given class, class little c is eta C. So what we're saying is a person's data come from the possibility that that person's in each class times what the model would say that class's data should look like. Okay? So oftentimes in the mixture model, eta C shows up as a probability. This other term, that's where things get crazy, right? If you have one piece of data, if you have like a normal distribution, like I talked about Pearson's crab data, fit 2 classes, this would just be a normal distribution, the mean and the variance. And so what we're trying to figure out is what proportion of crabs are in class 1 versus class 2. And then for people for crabs in class 1, the mean might be 10, variance might be 100. For crabs in class 2, the mean might be 5, variance might be 2, right? So you're trying to compare and contrast those two with it. Questions? All right.
Why do you call it mixture instead of just hierarchical?
Well, hierarchical model is really reserved for some very specific models in what we do. The same question would be, you could say the same thing about an IRT model. This is effectively an IRT model where we have discretized the latent variable, right? But would you call that a hierarchical model also? Yes, in some respects. You could say that people are nested, or items are nested with people. But here, mixture is basically because there are different sort of overlapping distributions the data might come from. And when you go and look at here, let me try to draw it here. I have an actual app for this. Let's see if I can make it work. All right. Okay, so let's imagine there are 2 classes, okay? Here's class 1, and here's class 2, right? And so what the conditional distribution is this thing right here. The mixture, the term mixture comes in where if you try to trace what the likelihood of this overall thing should look like, if you didn't observe all these right here, you'd say the distribution of the data itself come from a mixture of different groups or different distributions themselves. So that's why it's called a mixture. That's where the term comes from, because these other distributions that are in there are mixing together to produce the final marginal distribution of the data. So it's an odd term. I think the way that people typically finite mixture is sort of a term I think that came about the last 20, 25 years, where people originally started, particularly close to education, would be latent class analysis. We would call this a latent class because there's a class of people that have this, and another class of people that have that. Whereas mixture is looking at sort of the pooling of both of them together. We're on a break. Should we take a break real quick? 10 minutes? Think about this. Think about why we hate it. Or Lisa and I hate it entirely. But I said DCMs do this. Uh-oh. Am I going to hate on that too? There are no sacred thoughts.
It's like probability seems high.
I just hate in general.